Okay, so in this next two exercises, we have to find derivatives of the given functions but of all orders. Now this may sound impossible at first, because how many times can you keep on differentiating a function? Of all orders means of 100th order, 1000th order, we will see. So this 29th one, and after that we have 30 also. For that one also we have to do a similar thing. The function given is a polynomial function in x of degree 4. So let us start by differentiating and see what we get. So we will of course first find the first derivative by applying our usual differentiation rules, which just essentially means that we have to keep almost everything in this expression intact except the powers of x. They have to be differentiated. For example, differentiating the fourth power of x, we get 4x cubed, but that divided by 2 remains. Similarly, minus 3 over 2 is unchanged, and then we differentiate x square, we get 2x. Minus differentiating x, we get 1. Okay, so this is the first derivative. Or actually you can simplify this also, because a little simplification is there. If you do the little cancellations, you will get 2x cubed minus, cancelling these two 2's, we get 3x minus 1. So you can see one thing, that differentiating the original polynomial function which had degree 4, we now have again another polynomial function, but its degree is 3. So degree has been reduced by 1. This means that if we next find the second derivative, the degree will again be reduced by 1, and that actually is true. 2 times the derivative of x cubed is 3x square, minus 3 times the derivative of x is 1, minus the derivative of 1 is 0 by the constant rule. It's a good idea to write this because it shows that you know. So this ultimately becomes 6x square minus 3. So yes, from a cubic polynomial we have come down to a quadratic polynomial. Once more, if we differentiate, we get the third derivative. And also, do not forget that in this notation, this 3 appears over d in the numerator, and in the denominator the 3 appears over x. Although I am saying that this is numerator, this is denominator, actually this is not a fraction, I am just simply saying. So differentiating once more, we get 6 times, what's the derivative of x square? 2x minus 0. So the next polynomial is a linear polynomial, 12x. Then the fourth derivative. This is 12, because 12 times 1, and then as soon as you calculate the fifth derivative, you realize one thing, that you have got 0. After that, of course, also you can keep on differentiating, but nothing is going to change. 0 will remain 0. And that is why it makes sense to ask us to calculate derivatives of all orders, because the higher order derivatives all are 0. It's now clear that the sixth derivative is 0, the seventh derivative is 0, etc. That is, the nth derivative is 0 for all n greater than or equal to 6. If you want, you can write 5 here, but I am talking about the derivatives after this. So I put this range for n. Okay, so the first few derivatives are these polynomials gradually with gradually decreasing degree, but eventually that decreases so much that we get linear polynomial, constant polynomial, and then after that all the others are 0. Similarly, we have this 30th one. This one is a little simpler than that one in the sense that you have only one term, although it's a 5th degree polynomial. So let's just do this one also and see what we get. We have differentiating the 5th power, we get 5x to the power 4 divided by 120. I do not want to exactly cancel this, okay, not yet. I mean, of course we can do cancellation if we want and write another expression here, but say I don't want to, I want to keep the denominator 120. Let's see what we will get. Then d squared y dx squared, for that we will differentiate x to the power 4, so that will give us 5 times 4 x cube divided by 120. The 5 times 4 of course is 20. X cube divided by 120. Okay. What about the third derivative? The third derivative is, of course, it's obtained by differentiating x cube, so that gives us 3x square divided by 120. Divided by 120. Then the fourth one, (60 times 2x divided by 120. So we get 120 in the numerator. So this becomes x. All right. And then the 5th derivative is just obtained by just differentiating x with respect to x, so that gives us 1. And the very next derivative is 0. Clearly, yeah, this time I am just simply going to write directly dny dx to the power n is equal to 0 for all the higher values of n. Why did I just simply not do any cancellation here? Well, this is because, let's make an observation. The observation is that this 120 Did you see that eventually after doing enough differentiation, we ended up having 120 here. But how did we get 120? By gradually multiplying 5 with 4 and then with 3, 2, 1. So that means this 100, or this is something we already know, that this is nothing but 5 factorial. Also, the other observation is that when you differentiate this term 5 times, that this 5 factorial vanishes and you just have x. Why this observation is important, that we will not understand right now, but for now just know that the form of this function is something important. We will see this type of terms in some series which are going to be very important for us. Okay. So with that we just leave it. I am not going to say anything more on this. When its time comes, then we will recall that once we recognize this. So let us now see what we have next. A power of x where the exponent is a positive integer divided by the factorial of that exponent, it has some significance. Next, find the first and second derivatives. Of the functions in exercises 31 through 38. So let's see what the 31st one is. 31st one. So this one has the function y equal to x cube plus 7 divided by x. Now this is a function which we can simplify. Simplify in the sense that we can take it to a form which will be easier for us to differentiate. And also keep in mind we have to find the first derivative and second derivative. So let's first simplify the function itself. We just want to avoid the quotient rule. So we just divide by x. Doing that, we will have x squared plus 7 times x to the power minus 1. And when you write times and put a dot, put it in a central position. Don't put it below. Okay, that means decimal point. Yeah, this is where full stops, decimal points go. At the bottom. And the middle place is for the operations. Plus, multiplication, these things, subtraction. So this is in a very good form for us to apply the power rule. Keep in mind that we also have the power rule for powers where the exponents are negative integers. We also have that. Now, dy dx will be, the first one of course is going to be 2x, but then 7 times, although we already know what the derivative is going to be, but still let's apply the power rule. That will give us the exponent comes down and then you have to subtract 1 from it in the original power. So that's how you get 2x minus 7 times x to the power minus 2. We won't gain anything by writing it as 1 divided by x square. So I keep it like this because we have to differentiate it once again. Actually, I can put a comma here because I can continue my calculation. So differentiating 2x, we will get 2 minus 7, and now again we once more apply the power rule. So the minus 2 comes down and then it becomes minus 2 minus 1. So that way we get 2 plus 14 times x to the power minus 3. If you want, you can keep it like this, or you can also write 14 divided by x cube. I will keep it just like this. Okay, so these are the first and second derivatives. The 32nd one is also similar, so this I am not going to do. It has different names though for the independent and dependent variables. T square plus 5t minus 1 divided by t square. So I leave this to you, an exactly similar one. But note that here in the beginning itself you are getting t to the power minus 2, but there is no difficulty in applying the power rule because all you are getting are powers of t. Exponent may be negative, but that doesn't change the form of the derivative. Okay, so this one you do. Then 33. Here again new names, r and theta. Theta minus 1 times theta square plus theta plus 1 divided by theta cube. It looks very complicated at first, but if you recognize the numerator is in a form and there is a simple expression for this product. Once you recognize that, it becomes very easy. So I will just do the simplification and the differentiation I will leave to you. So we will start the solution like this. We have r equal to theta minus 1 times theta square plus theta plus 1 divided by theta cube. The numerator is simply theta cube minus 1. If you do not remember this, you can do the multiplication also, and then after some cancellations you will see that you are left with theta cube minus 1. So this means we have 1 minus theta to the power minus 3. This you have to differentiate again by using the power rule. But keep in mind, when you write the derivatives, do not forget that it's not always y and x. Here for example it's s and t, here it's r and theta. So accordingly you will also have to write the derivative notations using those variable names. So from this you do. Then 34. Here we have u equal to x square plus x times x square minus x plus 1 divided by x to the power 4. By now it must have become quite clear that it's better to always simplify a function if that's possible, as much as possible, before doing the differentiation. Although you have everything for you, even if you want to differentiate it in the form it is, you can do that. You can apply the quotient rule, product rule, but it will be very long. X to the power 4. You can do several things here. What I feel will be nice is to divide this by x square and this also by x square. That is, I am talking about this. Because the denominator is the fourth power of x. So that you have this, and then here after you do the division you get 1 minus x to the power minus 1 plus x to the power minus 2. And now if you want, you can choose to not multiply and now apply the product rule. So I don't know how successful, how convenient that is going to be, because we have to differentiate once more. Now I think, okay, hold on, I think it will be better if we multiply, because if we simply use the product rule, then we again have to anyway multiply. That's because we can't keep the derivative in that form. Again we have to differentiate. No? So multiplying this expression by 1 produces, of course, that expression itself minus 2 plus multiply by x to the power minus 1. So plus x to the power minus 1 minus, because we have minus here, this times this is x to the power minus 2 plus x to the power minus 3. Oh, okay, yeah, okay, yes. Multiplying this has been actually beneficial, because these two terms vanish. X to the power minus 2 minus x to the power minus 2, they also vanish, and you get 1 plus x to the power minus 3. So it's almost like this one, here you just have minus and here you have plus. Since you have to do this differentiation and you have to also do this differentiation, and after you differentiate once, this one will produce simply 0, this one will also produce 0. So there will simply be a difference of the sign, and then again you have to differentiate. So since it has been reduced to such a simple form, so I don't think I need to do this again. You just differentiate this once and then once more. Okay, so this also you do. In fact, this was the main thing. After this, it's a very simple task. I didn't actually know that it will come to this form ultimately. I thought I will get stuck here. So it also shows that the authors have not really chosen these exercises randomly, just simply thinking of some things. They have given these things very carefully. Next, 35. Yet other names. W equal to 1 plus 3z divided by 3z, or if you prefer to call it z, whatever you want to call it, it's just a variable. Please complete this unfinished ones, okay? And if you feel something is wrong or you want to get your answers checked, please write in the comment section. Minus z. Okay, is there any significant simplification that will be possible here? We can of course do one thing. Yeah, without first doing division, let's just first do the multiplication. Multiplying this by 1, we get 3 minus z, and then by 3z, we get 3 times 3, 9z minus 3z square divided by 3z, and then we do the division. So it will be z to the power minus 1 minus 1 divided by 3 plus 9 over 3 is 3 and z cancel out. So 3 minus 3 they cancel and we are left with z. Oh, the way I am writing these things, I have to very carefully write 3 and z, okay, so that we do not confuse between them. Okay, let me just do the differentiation in this case. The dependent variable is w and the independent is z. So this is going to be minus z to the power minus 2, because minus 1 comes down and you know usual stuff. This 2 will give you 0 and this one becomes minus 1. Okay, so this is the first derivative. Then the second one. This will not contribute anything, will be 0. What about this? Already we had a minus. Minus 2 comes down and z to the power minus 2 minus 1. So this is equal to 2z to the power minus 3. Okay, so that's the second derivative. Next, 36. W equal to z plus 1 times z minus 1 times z squared plus 1. Yeah, here also there is a significant simplification. If someone starts applying the product rule without first simplifying, it will be, you will get the answer ultimately, but it will be something very big. The form it is in right now, it's screaming for simplification, because z plus 1 times z minus 1 is z squared minus 1, and it doesn't stop here also, because this minus 1 times this plus 1 further gives us this. So again, just a power of the independent variable minus a constant. So it's almost like this in form. So this one I leave to you. You actually can see almost immediately what you are going to have as the first derivative. It will be 4z cube. And then the next one will be 4 times 3z square, that is 12z square. That's it. Okay, then 37. P equal to q square plus 3 divided by 12q times q to the power 4 minus 1 divided by q cube. All right. Here also hopefully we will have a simplification. Shall we do the multiplication first? Yeah, we can do the multiplication first in the numerator and in the denominator also, because if you do the divisions first, that won't give you any distinct advantage. So this is what we are going to do. 12 q to the power 4. You can choose to not write this step also. You can straight away do the multiplication. Q square times q to the power 4 is q to the power 6. A very common mistake that people do when multiplying such powers is to write q to the power 8. They think that 2 and 4 will get multiplied. No, no, no. When you are multiplying powers, the exponents get added. When you take a power of a power, then only the exponents get multiplied. If you have q square to the power 4, then only you multiply 2 and 4. Why? Because what does it mean? It means multiplying 4 copies of q square. And that again involves adding the exponents. So when you add 4 2's, you get 8. Okay, so that way you get 8, but that's not the case here. So 6 minus q square plus 3q to the power 4 minus 3. No simplification, but that's not a problem. I mean, no cancellation. And now we can do our division. So this will be, when you divide q to the power 6 by q to the power 4, you get q square. 1 over 12 q square minus 1 over 12 q to the power minus 2, because 2 minus 4. Just like multiplication adds the exponents, division tells us to subtract the exponent of the denominator from the one of the numerator. This one of course becomes plus 1 over 4 because q to the power 4 in both the numerator and denominator. Minus 3, oh so here also we have 3, so 1 over 4 times q to the power minus 4. Okay. So now if we differentiate once with respect to q, the dependent variable name is p, okay, not that. Then first we will get 2q divided by 12, then minus 1 over 12 times minus 2 times q to the power minus 3, subtract 1 from the exponent, plus 0 minus 1 over 4 times minus 4 times q to the power minus 5. So this becomes q divided by 6, minus and minus will give us plus, 2 divided by 12 is 1 divided by 6, but we also have q to the power minus 3 in the numerator, so that divided by 6. Minus minus will become plus, 4 and 4 will cancel out, so plus q to the power minus 5. So that's the first derivative. And the second derivative is, if you differentiate q, you get 1 over 6. Q to the power minus 3 will give you minus 3 times q to the power minus 4 divided by 6, and q to the power minus 5 gives you minus 5 times q to the power minus 6. So after simplification, this becomes 1 over 6. So after you do the cancellation, adjust sign everything, q to the power minus 4 divided by 2 minus 5 q to the power minus 6. If you want, you can also write 1 divided by 2 q to the power 4, and here minus 5 divided by q to the power 6. Some people do not like to see powers with negative exponent, okay, so they want to write as denominator. And finally we have 38, again p and q. The numerator is q square plus 3 and the denominator is this. Okay, so let's see what type of simplification we can possibly have here. Q square plus 3 divided by this. So we will have some cancellations, but will that ultimately give us anything simple? That's the question. If you simply expand these powers without thinking much, you get q cube minus 3q square plus 3q minus 1, and expanding this one we get q cube plus 3q square plus 3q ran out of space plus 1. Okay, it's yeah, I mean if I started from here I could have written 1 here, but you get the thing. This is the denominator. So after you do cancellation, what are the terms that we can cancel? Minus 3q square plus 3q square, minus 1 plus 1, the rest will stay. and will double actually q cube and q cube. Q square plus 3 divided by 2q cube plus 3q and 3q give us 6q, and others of course they vanish. Oh yes, yeah, now I see it. Now what we can do is that we can take 2q outside, then this one will become q square and this one will become 3, and then we have a cancellation. So it's just this. So such a complicated expression turns out to be equal to this after cancellation, simplification, everything. Now you can differentiate this 2 times, and that one of course I leave to you. It's so easy. So with that, let's just stop the video here itself. Tomorrow also we have our upload of our usual linear algebra. And since we have started solving exercises, and we have already solved the first 2 of the current section on this Jordan canonical form. So tomorrow we will solve the others. Others means we will see what comes next. So that's just it for tonight. See you tomorrow with linear algebra. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.